Here's a problem in projectile motion that involves a person throwing a ball or a shot put or a baseball or something like that from 1.8 meters above the ground, and their launch velocity is 12 meters per second at 40 degrees above the horizontal as shown. So typically a question like this might ask something like, how far does the shot put land from where it was thrown? So if you can imagine that parabolic trajectory the shot put's going to take is going to impact somewhere right about there, and the question then is what is this distance? How far is it going to go? We'll call it something like x sub m for x sub maximum, say, if you will. So as we try to emphasize throughout the course, oftentimes these projectile motion problems boil down to having good knowledge of the hang time of the ball. In other words, how long is this ball or shot put or whatever it is in the air in the first place? That usually comes from looking at the y equation, because the y equation involves the vertical motion of the ball. And so let's see if we can just go ahead and set that up and get that hang time out. So what I'll propose then is to use equation 1 in the y form, where we can say something like, well, the final position of the shot put is going to be over here at y is equal to 0. So let's say something like 0 is equal to 1.8. The 1.8 is the initial velocity, the initial height of the ball. So what I'm filling in is y is equal to y0 plus v0 y delta t plus the other term, the half at squared term out there. So I'm saying here's y, the final position is 0. Here's where it started at 1.8. Now the initial speed in the y direction is going to be the y component of the 12 meters per second that it was launched at. So 12 times the sine of 40 times delta t. And then lastly, always in the vertical direction, we have gravity, so we've got to get that in there. So we'll have a minus 1/2 g times delta t squared, something like that. So you go ahead and inspect the equation. I hope you can recognize the parts here. This is just y is equal to y0 plus v0 y delta t plus 1/2 a times delta t squared. I just filled in for this particular problem. Hang-up points typically involve signs like this and this, but the initial launch speed in the y direction is up. That's why this is positive, and of course gravity's down. That's why that's negative over there. So if you look at the Brown equation here, you have a quadratic equation in the variable t. Now you need to be able to solve that sort of thing, but if I do that here, I get a delta t about 1.4 seconds. So this ball is going to be in the air for 1.4 seconds. If you want to know what the range is now, you can fill in the equation 1 here once again, but for the x direction. In particular, x is going to be x naught, which is 0. Let's just say that the ball was initially launched from 0 right here. v0x is going to be 12 times the cosine of 40 times delta t. And normally we'd like to put a 1/2 at squared term on this, at delta t squared term on there, but there is no x acceleration in these problems. That term just drops out. And so once again, I'm filling in x equals x0 plus v0x delta t plus 1/2 a delta t squared, but of course no ax, and these are just all the other parts to it right here. So the 12 cosine 40 is the x component of the initial speed. So once again, the Brown equation right there, what do I put in for delta t? Well, that's the hang time. That's that link in the importance of the hang time in there. That's how long the ball is in the air. So after that amount of time has gone by, it's on the ground over here, and that's going to set its maximum range. So you can just plug in some numbers here and get v0x is going to be 12 times the cosine of 40 times delta t, which is the 1.4 seconds. So if you put all this together here, punch in your calculator or whatnot, you'll get the range of that projectile.